Uh, Good afternoon all. So today we'll continue the problems on partial differentiation. In the last video we have seen the first three problems. So let us see the fourth one. The fourth problem is that if we are given the function f expressed as x raised to y, we are asked to show that dou to f by dou x dou y is equal to dou to f by dou y dou x. So mixed second order partial derivatives for this function are equal. That is what we want to prove. So let us first obtain the expressions for dou f by dou x and dou f by dou y. So we are given f is equal to x raised to y. So that differentiating this f partially with respect to x, we shall get dou f by dou x equal to dou by dou x of x raised to y, and this is nothing but equal to y x raised to y minus 1. This is nothing but y x raised to y minus 1. So differentiating this dou f by dou x partially with respect to y, we shall get dou to f by dou y dou x, that is nothing but dou by dou y of dou f by dou x. So this is nothing but dou by dou y of y x raised to y minus 1. So here there are two terms containing y, and we want to differentiate this product of the two terms with respect to y. So we have to use the product rule for differentiation. So the differentiation works out to be equal to if we differentiate y, the differentiation of y with respect to y is 1. So it is x raised to y minus 1 plus keeping y constant, differentiate the term x raised to y minus 1 with respect to y. So this works out to be equal to differentiation will be x raised to y minus 1 into log of x. Differentiation of x raised to y minus 1 with respect to y is x raised to y minus 1 into log x. So this is dou to f by dou y dou x. So this is the expression for dou to f by dou y dou x. Similarly, we can obtain dou f by dou y. Differentiating f partially with respect to y, we get dou by dou y of x raised to y. So this is x raised to y into log of x. Differentiation of x raised to y with respect to y is x raised to y into log x. So this is dou f by dou y. Now we can differentiate this dou f by dou y partially with respect to x, so that we get the expression for dou to f by dou x dou y, that is dou by dou x of x raised to y into log of x. So this is it. Here there are two terms appearing in the product containing x, and we want to differentiate this product with respect to x, so that we can apply the product rule for differentiation. So differentiating first, we get y x raised to y minus 1 into log x as it is plus x raised to y as it is into differentiation of log x is 1 upon x. So this is equal to this term is x raised to y divided by x is nothing but x raised to y minus 1 plus the second term is y x raised to y minus 1 into log of x. So this is the expression for dou 2f by dou y dou x, and this is the expression for dou 2f by dou x dou y. So if we compare these two expressions, it is observed that what is observed from these two expressions? We observe that dou 2f by dou x dou y is nothing but equal to dou 2f by dou y dou x, and each is equal to x raised to y minus 1 plus y x raised to y minus 1 into log of x. So that is how we can prove that if f is equal to x raised to y, we can show that dou 2f by dou x dou y is equal to dou 2f by dou y dou x. So that is the fourth problem. So let us see the next one. See the fifth problem. Here we are given the function f expressed as a ln of x square plus y square. F is expressed as a ln of x square plus y square, and you are asked to show that fxy equal to fyx and also you are asked to show that the sum fxx plus fyy is equal to 0. You are asked to show that fxy equal to fyx and fxx plus fyy is equal to 0. That is what we want to prove here. So let us begin with function f. So we are given f as f is given to be equal to a ln of x square plus y square. So differentiate this f first partially with respect to x. We get fx equal to dou y dou x of a ln of x square plus y square. So this is equal to differentiation of this will be differentiation of ln of x square plus y square is 1 upon x square plus y square into differentiation of x square plus y square with respect to x is twice x. So this works out to be a upon x square plus y square into twice x. Right? So this is nothing but equal to twice ax divided by x square plus y square. This is nothing but twice ax divided by x square plus y square. This is the expression for fx. Similarly, we can differentiate f partially with respect to y. So we get fy equal to dou by dou y of a ln of x square plus y square. So again that differentiation with respect to y will be a upon x square plus y square into 2y, or that is nothing but twice ay divided by x square plus y square. So these are the expressions for fx and fy. Now we can differentiate fx partially with respect to y and differentiate fy partially with respect to x, so that we will get the expressions for fxy and fyx. So let us differentiate fx partially with respect to y. So we get fyx. So fyx will be equal to dou y of fx. Dou by dou y of fx, and fx is twice ax divided by x square plus y square. So differentiating this expression partially with respect to y, we get here we have to apply the quotient rule for differentiation. The quotient rule for differentiation is differentiation of numerator divided by denominator is dn dash minus n d dash upon d square. So this is the differentiation of the question. So using this formula here, denominator is x square plus y square as it is, into differentiation of numerator is 0. It is dou y of twice ax minus numerator as it is twice ax into differentiation of denominator is dou y of x square plus y square whole divided by denominator square. Denominator is x square plus y square brackets. So this term will vanish. So fyx will work out to be equal to. So this is nothing but equal to fyx will be equal to fyx. So fyx is equal to minus twice I have he term managed with, so it is twice minus twice ax into dou y of x square plus y square is twice y. So it is minus 4a, minus 4ax y. So we get this fxy is equal to this. So is it fxy or fyx? This is fxy, not fx. So fxy. That is dou by dou y of fx, and dou by dou y of fx is like this. So dou by dou y of fx is twice ax divided by x square plus y square. So this works out to be equal to minus twice ax divided by x square plus y square bracket square into 2y. So this is nothing but equal to minus 4axy divided by x square plus y square bracket square. So this is the expression for fx. Similarly, we can obtain the expression for fyx. So Similarly, we can obtain the expression for fyx. Fyx can be obtained. Okay, so we will obtain fyx here. Fyx is nothing but dou y dou x of fy, and fy is twice ay divided by x square plus y square. So differentiation of this, once again using this quotient formula for differentiation, we get this expression as, so this is equal to Kyle hai, this will be equal to dou by dou x of twice ay divided by x square plus y square. So this is minus twice ay minus twice ay divided by x square plus y square bracket square into 2x. So this works out to equal to minus 4axy divided by x square plus y square bracket square. So if we compare the expressions for fxy and fyx, fxy is minus 4axy divided by x square plus y square, and fyx is minus 4axy divided by x square plus y square bracket square. So what we can say here is that, therefore we can say that fxy is equal to fyx. So this is the first identity we have proved here. The first identity we have proved here. Now we want to prove that fxx plus fyy is equal to 0, the second identity. So for that purpose, we have these expressions for fx and fy. So starting from these expressions, now we can prove the second identity, that the sum of fxx and fyy is equal to 0. So if fx is equal to this expression twice ax divided by x square plus y square, this will imply fxx to be equal to differentiating twice ax divided by x square plus y square, once again partially with respect to x, we get dou by dou x of twice ax divided by x square plus y square. So this is fxx. So differentiating this, we get, again we have to use here the quotient rule for differentiation. So this is, or else you can apply the product rule also, doesn't matter. So this is twice a divided by x square plus y square minus twice ax divided by x square plus y square bracket square into twice x into twice x. So this is equal to twice a divided by x square plus y square minus 4ax square divided by x square plus y square bracket square. So this is the expression for fxx. Similarly, we can obtain the expression for fyy. So fyy is nothing but dou by dou y of fy. Fy is twice ay divided by x square plus y square. So this is equal to, again using the product rule for differentiation, we can express it as twice a divided by x square plus y square minus it is twice ay divided by x square plus y square bracket square into twice y. So this works out to be equal to, so this is equal to twice e divided by x square plus y square minus 4 y square divided by x square plus y square bracket square. So this is the expression for fxx and this is the expression for fyy. So now taking the addition of these two expressions, what will get, let us say. So fxx plus fyy is equal to fxx is twice a divided by x square plus y square minus 4a x square divided by x square plus y square bracket square plus fyy is twice a divided by x square plus y square minus 4a y square divided by x square plus y square bracket square. So this is the thing, right? Twice a upon x square plus y square and plus twice a upon x square plus y square gives us this gives, so fxx plus fyy is equal to 4a, so it is 4a upon x square plus y square. From these two terms we can take 4a upon x square plus y square bracket square common. So this is minus 4a upon x square plus y square bracket square common here. Bracket में ऐसे लग रहे हैं, so into bracket it is x square plus y square. So it is x square plus y square. So this x square plus y square will cancel with 1 x square plus y square here. So this works out to be equal to 4a upon x square plus y square minus 4a upon x square plus y square. So this is equal to 0. So we get fxx plus fyy is equal to 0, the second identity. So that is how we can prove the two identities for this function f equal to a ln of x square plus y square. First we have proved that fxy equal to fyx, and then we have proved that fxx plus fyy is equal to 0. So that is the fourth problem. Next, fifth problem. Next we shall see the sixth problem. So let us see the sixth problem. Next problem is you are asked to show that z is equal to f of x plus ct plus y of x minus ct is solution of dou 2z by dou x2 is equal to 1 upon c square dou 2z by dou t2. So you are asked to prove that this function z equal to f of x plus ct plus 5x minus ct is the solution of this differential equation. So whenever we want to prove that the given function is the solution of a certain differential equation, what we need to do is we have to start with the given solution. So here we are given that z is equal to f of x plus ct plus phi of x minus c. So let us differentiate this z partially with respect to x. So we get dou z by dou x. So dou z by dou x will be equal to f dash x plus ct plus phi dash x minus ct. This is dou z by dou x. And differentiating dou z by dou x once again partially with respect to x, we get dou z by dou x to be equal to f double dash x plus ct plus phi double dash x minus ct. So this is the expression for dou z by dou x. Similarly, we can differentiate z partially with respect to t. We get dou z by dou t to be equal to f dash c there. C into f dash x plus c minus c phi dash x minus c. This will be the differentiation of z partially with respect to t. So, and again differentiating dou z by dou t with respect to t partially, we get dou z by dou t to be equal to, again differentiating this partially with respect to t, we get c square f double dash x plus ct minus c square phi double dash x minus ct. And taking c square common, we can express it as c square into bracket f double dash x plus ct plus phi double dash, yes, this c square common here, minus minus will become plus here. So this minus c and into minus c, so it will become plus c square. So it is plus phi double dash x minus c. So what is this bracket? This bracket is nothing but dou z by dou x. This bracket is nothing but dou z by dou x. So using the value of this dou z by dou x here, we can express dou z by dou t is equal to c square into dou z by dou x. Or we can express this relation as dou z by dou x to be equal to 1 upon c square dou z by dou. So since what we did, we have started from the function z and we have arrived at the given differential equation. So what we can say here is that, say this is the equation 1 and this is the equation 2. So what we can say is that equation 1 is the solution of equation 2, because we have started from equation 1 and arrived at equation 2. So this is the solution of this differential equation. So equation 1 is the solution of equation 2. So with that we will stop here for this video, and we will continue the next problems in the next video.